Hello everyone, this is Mahmoud Al-Laythi. Today we will see how we can mathematically calculate the barycentric weights and the closest point on a triangle without having an actual mesh in the scene. And this is very useful if you want to import like a deformer weights in a world space without having the old mesh. Like for example, if you have a mesh and you exported the skin weights and when you procedurally rebuild the rig, the new model has a different topology. So you want to import the old weights in world space. Or even if you want to create like a wrap deformer that using a point cloud or using anything other than a mesh. And this method also works on meshes. So if you want to calculate these data from like UVs, anything without having the actual mesh in the scene, or if you don't want to use the Maya intersector for any reason. So very quickly, let's see what we will do today. So first thing that we will need to do is to get the closest point on this triangle. Then we will need to calculate the barycentric coordinates. And just to recap what the barycentric coordinates are, they are weights that if you apply these weights, like if, for example, if you want to get this point from these 3 points, you will be able to multiply the weights that you will calculate with these 3 point positions, and it will reproduce this point. So if you want to create a wrap deformer, this is the first thing that you need to do. And if this is like a skin deformer or like a skin cluster weights you want to import, in order to get like this is the new mesh point, and there is no you will get the closest point here on these three and interpolate the weights to it. So let's see how we will write this down. So the first thing that we should do is we could create the Maya intersector, which is the typical way to get the closest point on any mesh, just to compare the values and see that we are going to the right direction. So first, let's get the position of this transform here. So let's say P equal like open Maya endpoint. Here I'm just creating an endpoint out of the transformations of this sphere here. Then we will need to create the Maya intersector. So let's say intersector equal open Maya m mesh intersector, and we will need to create this intersector. So creates, like if you look at the documentation of create, let's run this one. So creates takes m object of the mesh and the matrix, so you bring everything to local space. In order to do this, we will need to get the m object of the mesh. So let's say dag mesh, and let's get the create an M selection list, add the ref plan in it, and get the DAG path and extend to the shape. So we want the mesh itself. So this is the DAG path. So we need the node, and also we will need the matrix. We can get the matrix from the DAG path. So this dot exclude. And if you're not sure, you can always get the help, and you will find exclusive matrix here. So let's add that. So if we look at the intersector here and what are the what you can get from it, you can get the closest point, which is the first thing that we need to do on our method. So get closest point return what called endpoint on mesh. So let's say point on mesh equal the intersector dot get closest point, and we want to query the P. So if we run everything here, this is point on a mesh. So if you look at inside the point on mesh, what you can get from it, you can get the point itself in 3D and get the barycentric coordinates. So as I said, if you do have the mesh here, It's very, very easy to using the intersector to get the closest point on the mesh and also get the pericentric weights of this point. But as I said, if you have just a point cloud or if you exported these weights like outside of Maya and you don't have the mesh anymore, for sure you still can import the old mesh and use Maya to do that. But if you want to do this procedurally and very fast, this is a very neat way to do it. So let's print here some information about this um, endpoint on mesh. So, and also we can snap this small sphere to the point. So here I print, let's remove the indexes. I will show you later. So this is the Maya one, right? So this is the Maya way, and this is the barycentric coordinates of this point. And here I will snap this geometry here to whatever position this thing give us. So if we run it here, and just to clarify how the pericentric coordinates works before we write our own math to get it. So basically, when you have a point on the triangle, you create 3 triangles out from this point to the other 3 points of the triangle. And this area of the triangle, the ratio of this area of the triangle on the whole triangle give you the weights for A. And this triangle ratio to the whole triangle give you C. And 1 minus A weights and B weights will give you the 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 last weight. So the sum of all of them has to be 1. So you couldn't have a negative value. If you do have a negative value, that means your point is outside of the triangle. And we will see how we can deal with this later when we write our own code. Maya already has a very neat way to get the closest point on the mesh. So if we run this again, it will detect this is the closest point. And I will show you how I was able to get this with my own code. So let's start to write our own algorithm here. So as we understood that we will always need to get the area of the triangle. So let's do this first. So here, custom barycentric. It's not custom. So then let's first thing. So this is how we will do it. We will get any 2 vectors from any point here, and we will get the normals of this triangle, and you will see why I went to this method. It's very easy mathematically, and because of we need the normals for other calculation, and second, the length of this vector here, the normal vector, is twice the size or twice the area of the triangle. So I will show you now. So let's say we want to get AB. First, we need to get the 3 points. So we will do it as we did on the P here. So here I just paste some code so we don't waste time writing this simple thing. So we need to get the vector from A to B. So it will be B minus A, and also the vector between, and then let's get AC, which will be C minus A. So now we have these 2 vectors. If we get the cross product of these 2 vectors here, then let's get the normal of this, which will be AB cross product AC. So as we said earlier, that the normal, the length of this normal will be twice the size, the area of the triangle. So this should be the length, the area of this triangle. So then we need to get the other 3 triangles areas and get the ratio on everything. So we will do the same. We will get 2 vectors here and get the normal, and this normal length will get the ratio of this length to everything. So we don't need to multiply everything by half every time. So this is the area. We know that this is twice the area, but everything will have the same factor. So in my tools, I always like sort these three indexes or points or whatever based on whatever you are going to do in like sort them based on distance to the point. So it will make a lot of other calculation easier as we will see later. So right now I will just get the point from my point to, let's say, this, like let's get this vector, for example. So let's say CP will equal C negative P. After we sort them, C will be the farthest, and it will make some calculation easier later, as you will see. So let's get the area of PCB, which is this triangle here. Let's mark it with another line. This is what we are calculating. So we get CB, right? And then we need to get the cross product in order to calculate this properly. So we will get the second vector, which will be PB, which will be B negative P. And we want to get the cross product of this one to CP, the one that we just calculated here. And there we want to get the length of this one. So this will be the smaller triangle area, or twice the area. So now the ratio for A, or like A weight, and we can call it U. Usually there is alpha, beta, gamma. There is a lot of other convention for the barycentric. I stick with U, V, and W. So this will be the area of this one divided by the area here. So this is the weight for A. Assuming that this point is on the mesh, we will see right now that we will end up having negative values because this is not on the plane, and we will see how we can get it easily on the plane. It will need a little bit of math. But we calculated the barycentric first because like having a negative value in the barycentric weights will tell us that the point is not on the mesh, and we will see how we can get it on the mesh very easily. And now let's calculate the other area, and the other area will be PCA. So this is the P, and we want to get this one to get this weight, right? So this will be equal to CP cross product A. I'm just moving a little bit faster here. Dot length. So V will equal the area of PCA divided by the area. And we don't need to get the W using the same method, because as we know, we have to have everything total to 1. So we can say W equal 1 negative U negative V, right? So after we run this, we will see that the W is negative because this point is outside of the mesh. So just to make sure that our math is correct, let's put everything on the grid here. Let's remove the Y translation, and let's put this one on the grid. So now we make sure that this point is on the triangle, and let's run everything here. So as you know that we made sure that here with the intersector we snap it to the point closest, which the same because it's on the mesh. So now we will see that the W is positive and V is positive. and u is positive. So here let's print our coordinates. So let's remove Maya here, and let's print u v w. So now as you see here, because as I said, we will sort them, but it's the same values here. And Maya don't give you the W because it assumed that you will do the same thing here. So now we need to do, the first thing that we need to do is get the closest point on the mesh using our math. So we need to project this point on the plane. I will go through the math very briefly. It's very easy to do like a very simple Google search on like projecting point on a plane. But just to understand what I'm writing in the code, what we need to do is first you need to get the normal of this triangle. That's why I told you in the beginning we will use this method on getting the triangle area because we need the normals anyway. Um, so after you get the normals of the triangle, you need to get from any point on the mesh, like a vector to your point. So let's say this is x vector, let's say, and this is your normal, right? And this is your normal, and you want to project this one here. And very like easy way to put it, like the projection is basically like you cast some light here, like a directional light, and the shadow and this directional light is perpendicular to your normal, and the shadow of your light is the vector that you need, is the projection. So this is projection x vector. And as you see, the projection of vector x is part of the normal. So projection x is something multiplied like a scalar multiplied to your normal, right? And we know that we have x, right? And we have n, but we don't have the scalar. There is something very interesting here. This vector here, this vector that whatever send us to here, this one is perpendicular to it for sure. And knowing that this vector here, is perpendicular to it is very interesting. This is how we will solve this problem. So let's say let's get what is this vector exactly. This vector is like the projection minus x, right? So if you subtract these two from each other, it will give you this vector. So let's write it like this. Let's write it like let's have another color here. Let's say x vector x, which what we know already. And if we subtract it from its projection, which will be like a scalar to n, right? A scalar to vector n. This is the projection. This is what we are after, but we will see how we will get C right away. So this is your projection. If you subtract it, it will give you a vector that is perpendicular to this one. So if you multiply this perpendicular one with the vector, with n, it will be equal 0. And this is we know for a fact, because this we know for sure this is perpendicular, so any dot product will be 0. So let's multiply this inside here, so it will be xn. It's like this is a dot product, and when you put this here, we know this is a scalar, and you multiply a vector here, so this is another dot product here, so it will be negative c n n. So you can write it like this because everything here is a scalar. This equals 0, right? So if you send this here, it will be xn equal c n n, And now if you want to solve for C, so everything will be on n. We run out of space, but you get the idea. And we will remove an n from here. So now we get C. So we know that C, if we replace here C with this, because this is C, so it will be like the scalar that we want will be x dot product n divided by n dot product n, and this is your vector here. So now you scale the vector here. So if we want to very easily write it in the code, and also let's hook it in a function so it's easy to use later. So let's say define get projection A, let's say A to P or to B or whatever. A is a vector and B is another vector. So in our case, A will be like this one, and P, and oh, I forgot to mention why we want to get this vector, because if you see, if we subtract this vector from our point, you will end up on the mesh. So this is how we will get the closest point on the mesh. So then let's write down this here. So we will say A dot product B divided by, where's the division, divided by n dot product n, and all of this multiplied by n, or sorry, b in our case here. I just b, b, b. So it's very simple to get it if you understand the math. So return this. So each time it's easy to put this everywhere, but just to understand why what this is. So let's clean everything here, and let's try this in our math. So here, instead of using the p directly, we will override the p here. So we will say p equal any point on the mesh negative the p. So we will say p, sorry, it's uppercase p subtracted from a, and the other one that we want to project on is the normal. So we didn't declare it. I think we need to put this into brackets. I'm pretty sure that we are missing brackets somewhere. Also this, we need to force this to calculate first. Then this should work. Yeah. So this is the new p, and as you see, it has no y value, but maybe it was an old one, and we need to put this in an endpoint because this will return a vector here. So let's put this in an endpoint and use the same X form here to snap our cyan point to this point, so we make sure this is also correct. So here, this is Maya's, and we want to replace this one here. So let's recap what we did here. We forgot a point. So this is the vector that goes up from here to here, right? We need to use this vector to subtract it from the original point. So we forgot to do this. So this return a vector. Let's do it like this. Let's say Cn, or maybe let's say P projection will be this one, and you need to subtract this point. So let's convert it here to m vector to make it easier for us. So I just to make the subtraction easy, and then subtract it from this projection here. So this will give us the new point on the mesh, and it doesn't know this. And now it snaps here because of P holding an old information. So if we run everything here, now it's correct. Let's try it with like different positions. Let's make this one like this, for example, and let's run everything again. So as you see, it will keep working until you leave the plane, because we just get the normal, and we from this normal we project it back. So if we move it outside of the plane here and do this, as you see, ours is just projecting it on like infinite plane, but Maya's just stick to the triangle, and we will see how we will do this right now. So as we did this with the plane, right now, like we will see that we have a negative value here, and this is not good. So what we will do is we need to put everything here in a function so we make it easy for us. And if this function return negative, we will need to project again. So let me show you. This is how I solve it. It's not necessarily the best way, but this is the main thing I would like to share with you guys now. So what I do is we already project from the normals down, right? And now this is outside of this plane. So the second thing you will do here is you will get like a cross product on this vector here, which will be the normal and the closest vector. And we will see how we will get the closest vector to our vector in a second here. So let's clean everything. We have the normal and we have this vector here. If we get the cross product of it and do the same thing here again, and we project this back, it will end up in the correct position. So first, let's clean the code and make like a neat function to do that. So let's do this very quickly. So let's say here, get barycentric chord, and let's pass A, B, C. These are the triangle, and we will pass P. Okay, and here, let's do this. And in here, at the end, we forgot to define. At the end, we need to return the U and V and W, and also the new point, which is the point that we projected on the mesh, and now it's P, right? So if we did this right now, we need to move this outside of the function, and we will use it later. And let's put the declaration here. So now, and let's put all the points together. So now the points, this is a triangle, the point, and the Maya intersector 1, just for comparison. And here, this is using our method to get the barycentric coordinates. And we will say weights and the new point. Let's call it P project or whatever. So if we run everything here, this should be correct. No errors. Let's try this one. So this is accurate, and now we have the correct values here, as you see. So the second thing that we need to do in order to project the other one, first we need to sort these points based on the distance. So there's many ways to do this. The way that I will do it, so first let's give it because this in your situation you will need to also track when you sort. You need to track the indexes that you sort. So for example, let's give this just for completion's sake, like anything, this should be integers, like the index or like the point ID. But let's just give them here A, B, C, so we can track how we sort them. And then we will need to get the distances, this list, for example, and we will from each we will iterate through the points and get the distance from this one to each one and sort that. So let's say p dot distance2. Distance2 is like a function inside the Maya point endpoint. It will give you like any the distance between any point to this point. So let's say vertex point or ID point or whatever for VP in, and let's put A, B, C here. So this is the list, and we need to sort everything here based on this list. So first let's sort the indexes. So let's say the indexes equal sorted, and then we need to sort the indexes, and the key will be, we will need to create a lambda function. If you're not familiar with how the key sorted works, it's very with very simple search on the internet. I will go through it very easily, very quickly here. So basically, the key here, it will call a function and it will return each element in this function and the call greater than on it to get the sorting. So you need this lambda to return the corresponding distance of this one. So this will return the first index, which will be A. So you need to get the distance list, and you here need to pass the index of A. So let's say indexes. So indexes is a list, right? We will call on this list an index method here and pass X. So this is a list. This is a method inside any Python lists that return what is the index of this element. Calling this indexes make it a bit confusing, but you get the idea, hopefully. So this will return the corresponding distance for this index. So if you did this here, it will tell you it's ACB. A is the closest, and so on and so forth. Like if we put it here in B, for example, just to make sure this is what we want here. So we know it's BAC. If we run everything again and check this, it's BAC. So now we sort them, and now we will need to sort the points themselves. So let's pass them in a list, and let's call it sorted points, or triangle points basically. And then let's put them points here will be A, B, C, and we will do exactly the same here. So we need to declare this. So this is the endpoint of this sorted. Now we can just directly pass this here, but just to keep track of everything, let's call it this A underscore B underscore C underscore. So in your code, you don't need to do this. It just here we can compare and debug. But at the end, I would recommend just you override the value. And also, if you are using C++, you won't declare another like part in the memory just for this. So here now we made sure that each time we call A here, A is the closest to this, and you will see now why. So we should say here, if any of these values is, so let's say W is lower than 0, and and oh sorry, or so if it's lower than 0 or greater than 1, we should do something, right? Because this means it's outside of the like this endpoint that we projected is outside of the triangle. So let's put this here, 1, and we need to do this for everyone in uh, each element. So let's open a big bracket here and say or. So this will be U V. So any of them. So any of these values are outside of this boundary, we should project again using the method that we just clarified earlier. So just right now, let's just let me comment this one here, because right now A is not the closest. It will be a little bit confusing. So let's do this. So now we know that A is the closest, right? So let's do it again here. So what we need to write here now is we need to get like a vector from the closest point to this point. So let's say AP will equal to P negative A. And now this is this vector here, because this is the projected point, because this is the case that we are trying to solve now. And let me just make the case. So we want to project this here now. So we know for sure that A is the closest because we already sorted this. So we getting this vector here, and we already know the normals, right? So this is the normal. We need to get this vector here. We could say, okay, it will be the vector, the other vector will be, let's say, um, a minus b, because we sorted, so we make sure that b is the closest, is the second closest. But if you see here, B might not be the closest, C might be the second closest. So this is the closest, this is the second, this is the third. But you need this vector, the closest vector. So in order to do this, let's say vector to use will be, this is the vector that we need to project, right? This is small one here. We need to project it here, but we need to project it on the correct vector. So in order to do this, we will check if the AB vector, the one that we already get here, let's say how you get this very easily. Let's think about it for a second. This is an angle, right? And you can get this angle by the dot product. So we need to get the dot product of this vector and this one and this one and this one here. So the greater dot product is lower angle and vice versa. So you need to get the greater dot product, which means like the vector is generally in the same direction. So the vector to use will be AB if, just if AB dot product AP is greater than AC, which is this one, dot product to AP. Else, like if it's not greater, use AC for sure. And now you need to get, you have the normal and you have the vector that you know now that it's the closest vector to A. And then you need to get the cross product of this one. So let's say the cross product normal will equal to the vector to use cross product. Where is it? Cross product, the normal. And you need to project this point here, this vector, to the cross product and subtract it from the P in order to move this point back here. So let's do it in one line. Let's say P equal to openMaya.endpoint endpoint, just convert it in one line, and let's convert the point to vector to easily subtract it. I think now you can subtract the endpoint from mVector, but it's just confusing to me. It's cleaner that way. And now we need to use our function here to get the projected one. So you need to get the projection of your point, which your vector, which is AP. You need to project this vector, AP, to the cross normal that you just calculated, right? So this is the vector, this vector here, as we saw earlier in the video, and this is the point. So now you will move this point here, and then you need to return the same function again. So you need to call it, so it will be a little bit recursive, but the issue with like one negative u and v, you might run with some rounding issue. This is what I faced earlier. So what we will do here is we will add another argument here to just not keep recursively calling the function if this is like very close to zero. Sometimes it's like this, and or maybe something like this. So instead of doing this multiple times and just try to find like the correct threshold, we will just put an argument here. Let's say recursive equal false, and by default it will always be recursive. Sorry, true by default. And when we call it again inside the function, we will make it false. And here we will say and recursive. So we make sure that we just recall the function once, because sometimes, yeah, when it's very close to zero, it won't be very good. So here I passed the new point, which is projected, and it will recreate the barycentric weights again and return the proper P second time. And here, when you project here, and now you can say here also if not recursive. Let's just erase. So let's do this. So you just call it once because you need to do this one time too, right? You don't need to do it multiple times, just to save some processing. So this will return the proper thing. So let's try it now. So B, oh, we didn't pass both. We just subtracted. Small typo. Yep. So now we will successfully project this back. And as you see here, this is very close to the Maya one, and this is very, very close to the Maya one. It even went to like a lot of rounding. But this one, as you see, it's slightly different because, but E negative 17, it's almost zero. So, yep. Now, if we are outside here, it gives us exactly the same values as Maya. Here. So here I found like a very interesting thing here, that when we did this once here, this ended up in another plane, and because like we are projecting it in the infinite plane, So you will always need to do this again. So now if it's already on this, it will be always correct, and it will snap to the correct vector even if the other point is closer. So I hope you find this useful. It was a small thing, but it took like 45 minutes. See you in the next video. See you.